Hey, what's up guys? My name is Andrew and today I'm going to be presenting on the paper titled Error Correcting Output Codes Improve Probability Estimation and Adversarial Robustness of Deep Neural Networks. First, for a quick overview, so in this paper, the authors present an output-based adversarial defense strategy that can be used in conjunction with input and model-based strategies. An example of an input-based strategy would be using a detector network to detect adversarial examples, and an example of a model-based strategy would be adversarial retraining. So one could theoretically combine the strategy proposed in this paper with a detector network and adversarial retraining to achieve enhanced robustness. And in particular, the authors suggest applying error correcting output codes to encode the predictions of the model in order to provide resilience against LP norm based adversarial attacks. First, for some quick background, so in a in a multi-class class in a multi-class classification setting with M classes, the standard encoding scheme is one hot encoding. So in one hot encoding, the kth class is represented by a binary vector that has a 1 at the kth index and zeros everywhere else. If we stack all of these one hot vectors on top of each other, we get an M by M identity matrix, which forms the quote unquote code book of the one hot encoding scheme. And we will denote the choice of code book using the letters C. So for every example, our model will output an M length logic vector denoted by the letter Z. This vector is also called the logic vector. The softmax function can then be applied to the vector Z to decode it into a predicted probability distribution over classes. So here P sub psi of K gives the predicted probability of class K under softmax decoding. An important concept related to error correcting output codes is Hamming distance. So the Hamming distance of two arbitrary binary vectors is the number of positions where their bits differ. And the Hamming distance of a codebook is just the minimum Hamming distance between all pairs of vectors in the codebook. So here in this example, the Hamming distance between the class for police and the class for doctor is 2, because as you can see here, the encoded vectors differ in the first two positions. Similarly, the Hamming distance of this codebook, so this entire matrix, is also 2 because all pairs of class vectors have Hamming distance 2, which should be easy to verify. Okay, so now we can talk about the main contribution of this paper. The authors provide two main ways to enhance adversarial robustness. The first is to use a more robust encoding scheme than one-hot encoding. So concretely, this would be one that results in a codebook with a greater Hamming distance than 2. Secondly, they propose using a more robust decoding function than softmax. And concretely, this means using a decoding function that is less sensitive to small perturbations in any individual logic, which just means that if any single component of the output vector Z is perturbed, the prediction of the model won't change greatly. And here I'll provide some mathematical intuition for what the authors are trying to do. So Taylor's theorem states that when we perturb the input x by a small amount delta x, then the amount that the output is perturbed, delta z, is proportional of the Jacobian j of the output with respect to the input dotted with the input, or the change in the input. So most existing adversarial defense strategies try to reduce the magnitude of this j, as doing that would also decrease the magnitude of delta z. But instead, the authors try to keep the magnitude of j constant in this paper, but they instead increase the delta z required for the model to change its prediction, and this results in the adversary needing to induce a larger delta x in order to change the prediction of the model. So on to the first main idea, which is instead of using the softmax decoding scheme we saw earlier, we can instead use what the authors call sigmoid decoding, which is parameterized by this function sigma. And this sigma function can be any S-shaped function that outputs between -1 and 1. So for example, the tan h function. And it outputs between -1 and 1 because we're using -1, 1 binary instead of 0, 1 binary. And this sigma function essentially interpolates a logit into a bit. And so intuitively, if we consider that C takes values between -1 and 1, then if our output Z more closely matches the class vector C sub k at more positions, this results in a greater dot product between sigma of Z and C sub k, which means that greater probability mass will be assigned to class K under sigmoid decoding. So yeah, essentially this sigmoid decoding function and this softmax decoding function have similar purposes, which is to convert a logit vector into a probability distribution. But as we'll see later, this sigmoid decoding function sort of does this interpolation more smoothly and leads to more robust decision boundaries. Okay, so essentially what this sigmoid decoding function is doing is adding padding to the decision boundary of our model, thus making it less susceptible to adversarial perturbations, as can be seen in these figures. So this is a two-class classification setting where red indicates the model predicts a high probability of class 0, and blue indicates a low probability of class 0, and therefore a high probability of class 1. So, and figure A is using softmax decoding, whereas figure B is using the aforementioned sigmoid decoding. And as we can see here, compared to softmax decoding, sigmoid decoding results in a much larger region where the model is unsure of its predictions, and this unsure region is denoted by this green here, where the model is about as sure of the example being classified as class 0 versus 1. And yeah, so we can see whereas the softmax decoding scheme changes rapidly between being absolutely certain of class 0 to being absolutely certain of class 1, the sigmoid decoding scheme reserves much more room for uncertainty. So it kind of gradually shifts its prediction over to class 1 instead of having this rapid shift we see here. And the third figure illustrates this enhanced robustness. So this magenta example here would be classified as class 0 for both the softmax and sigmoid decoding schemes. However, individual perturbations of an individual logit, which is denoted by these black arrows, would result in a misclassification under the softmax decoding scheme, but it would not under the sigmoid decoding scheme. It is only when you modify both Z sub 0 and Z sub 1, so when you modify both logits as denoted by this gray arrow, that you end up with a misclassification under the sigmoid decoding scheme. Oh, also I should mention that the sigmoid decoding scheme is still using the one-hot encoding, which the softmax decoding is also using. Okay, the second main idea presented is to use a Hadamard codebook instead of a one-hot codebook. So recall that the Hamming distance of the one-hot codebook is only 2. Practically, this means that the adversary needs to flip only a single logit in order to cause the model to change its prediction, as we saw on the previous slide. In contrast, the Hamming distance of the Hadamard codebook for m classes is m over 2. And so a greater Hamming distance of a codebook means that more bit flips are required to change the predicted class of the model because the class vectors are now further apart in binary space. Oh, and here is an example of a Hadamard matrix for 4 classes. So as we can see, the Hamming distance between the first row and the second row is 2 because the vectors differ here, and the Hamming distance between this row and this row is also 2 because they differ here, and you can verify that indeed the Hamming distance of this matrix H sub 4 is 2. And this is the recursive definition for the Hadamard matrix. Okay, so if we combine Hadamard encoding with sigmoid decoding, we get fantastic results. Here the colors mean the same as they did before, where red indicates a high confidence in class 0 and blue indicates a low confidence in class 0. These leftmost plots were formed using one-hot encoding and softmax encoding. The middle plots were formed using one-hot encoding and sigmoid decoding. And the right-hand plots are using Hadamard encoding with sigmoid decoding. So, and the bottom row is just the top row, but rotated to get a different view. So if we think of the decoding function as performing a sort of nearest neighbor search in Z space in order to find the most probable class given an output logit vector Z, then the combination of Hadamard encoding and sigmoid decoding, as shown on the right, effectively stretches out the region around each class in Z space, making it so that the adversary needs to perturb Z much more in order to change the prediction for any example. So yeah, you can kind of, if we look at the region here for one hot with softmax, we're essentially taking this yellow and red region over here and stretching it out using Hadamard with sigmoid decoding. And this means that in order to get to this blue region, we now have to travel much further in Z space. So this is good for having enhanced robustness. Another thing that the authors mentioned briefly is the concept of bit independence. So in a typical deep neural network, the output layer outputs all the bits of the output code. However, the authors instead propose to use an ensemble of networks, each trained on a disjoint subset of the classes, in order to limit correlations between output bits. So instead of having one neural network produce the entire output vector Z, we would have multiple neural networks, each producing a subset of Z for a subset of classes. And then when we combine the outputs of all of these neural networks, we get the final output. And by doing this, we limit the correlations between each of the output bits. And this results in greater accuracy. So experimentally, these plots show the effects of different choices of codebook, code length, and decoding scheme on the distribution over examples of the probability distribution assigned to the most probable class, where each line in the plot is produced by a different model. So figure 8 depicts this distribution over benign examples, B over adversarial examples, and C over randomly generated examples. Concretely, what this means is that for benign examples, almost all models shown here by these colored lines put over 90% probability mass in the most probable class. So almost all models are over 90% sure of their prediction, essentially. Okay, so now let's compare the performance of two models. The first being the softmax model depicted by this light pink line that uses one hot encoding and softmax encoding, and the the 1016 model, which uses Hadamard encoding and sigmoid decoding. So both of the models are confident on benign examples, which is desirable. But for adversarial and random examples, we can see that 1016 is much less sure about the most probable class than softmax is. We can see that even when the examples are adversarial, softmax is still very over 90% certain that, or softmax is still usually over 90% certain that the most probable class is the correct one, whereas 1016 has a much flatter distribution, meaning that it's much less sure on average of the most probable class being the correct one, which is good because this is an adversarial example. Okay, so here are more plots plotting model accuracy on adversarial examples on the y-axis versus perturbation strength on the x-axis. And the left plot is generated on the MNIST dataset, and the right plot is generated on the CFAR dataset. So we can see here that the softmax decoding scheme, the softmax model using one hot encoding and softmax decoding degrades, its performance degrades at a much lower perturbation strength than the 1016 model. So when the perturbation strength is only 0.3, the softmax model has almost zero accuracy, whereas the 1016 model is still preserving around over 90% accuracy on adversarial examples, which shows that using Hadamard encoding with sigmoid decoding does indeed improve robustness on adversarial examples. Okay, thank you for listening to my presentation, and I hope you have a nice rest of your day. Here are the references I used in creating this presentation. And yeah, stay safe.